from here, and then we can continue. Okay, so here we have the two control loops for the generator. One through the governor, and here you can control. And of course, this P mechanical is coming from a turbine, and then you have here a steam, and you have a steam valve here. So this governor will control the valve opening. So if you control the steam comes to the turbine here, you can control the mechanical power input to the generator. So this is the first loop. Second loop, you have here terminal voltage. You can measure the terminal voltage, and you can, through the automatic voltage regulator, you can control the excitation. The flux comes here to the stator winding. So you have two control loops here. Okay, so you have the generator, you have the mechanical control loop, and you have also voltage control loop. So all these elements will be modeled. The turbine will be modeled, automatic voltage regulator, and the generator, of course, the governor, and also if you need to stabilize, if you need to add a supplementary control, whether you can have here like another controller. This is called power system stabilizer, and this is the main issue in our course. What is the impact of this power system stabilizer, and how to design it in order to improve the power system stability. Now, power system stability is you have several stability in power system. If you have any idea about what are the stability problems that we have in power system? When I ask a question, if you have an answer, please raise your hand, and then I will call you to answer. So, and we need, as I mentioned, I need more interaction during the class. So when we say power system stability, what do you think about power system stability? Or what are the types of the stability that we have in power system? Is it only one stability, or we have different types of stability? Saad Ahmed? Saad Ahmed? عبد العزيز خالد الجهني.
Yes, Doctor.
Yes.
I think stability refers to the ability of the system to get back to the steady state condition after a fault or an incident that happens, or a change in the load or something.
Yes, absolutely right. This is the definition of the stability. The system is coming back to the steady state condition after exposed to a disturbance or so. My question is, what are the stability problems that we have in power system in general? Saad Ahmed?
Yes, Doctor. Can you hear me now?
Yes, we hear you.
Okay. There could be different categories in stability. One of them is voltage stability. There could be, I think, frequency stability, and I think a few more, but it's just not coming to my mind right now. Frequency stability, voltage stability.
طيب, let us see Ali Ramadan. Do you want to add one type of stability more?
Yes, doctor. Are you talking about like input-output stability, like bounded input, bounded output? So is that what you are looking for?
I'm looking for the third type of stability in power system, which is angle stability. This is called the angle stability. And actually, we will cover mainly this type of stability. How the rotor speed and rotor angle change with time. How to get delta of t after the disturbance. How the omega of t and delta of t behaves. We will solve what we call the swing equation. And this is actually covered in 520. Maybe you covered in 520 what we call the swing equation. Swing equation is simply m times the acceleration d square delta by dt square equal to P mechanical minus P electrical, or mechanical torque minus electrical torque. So we need to solve this. We need to find delta of t. And we will see delta of t. If we have delta of t, if we have a disturbance here happen at this moment, then the delta may be increased, and then coming back down, and ups, downs, overshot, undershot, and then it settled down to its steady state value, maybe the same value or another value. It depends on the disturbance, whether it is a fault or a pulse. If it is a step disturbance, then we will move to another steady state point. Maybe we can settle down here somewhere. So this is delta of t. So we need to solve this swing equation. And this is what you have covered in 520. You start, solving this swing equation using either numerical solution, iterative solution, Runge-Kutta method, Euler method, trapezoidal method, numerical integration methods in general. Or you can solve the swing equation using a graphical method, which is the equal area criteria. This equal area criteria is the solution of the one way to also to solve the swing equation and to check whether the system is stable or unstable. So if this is the case, the system is stable. If we have like this as a delta of t, in this case, definitely system is unstable. Omar Salman, do you have a question, Omar?
Yes, doctor. Yes.
Yes.
We mentioned the last angle stability. So I want to know if it is the rotor angle or is the one called the voltage angle, and which of these is actually most important in talking about in power system stability.
Okay, this is rotor angle, by the way. This delta is a rotor angle.
Okay.
Rotor angle.
Okay.
This voltage stability is simply you have a voltage here, V, and the system loading in terms of power. Okay? If there is no loading, you can expect the voltage here to be 1.05, for example, at a certain bus. If you start increasing the loading at the bus, what do you expect regarding the voltage? What do you expect?
The voltage will decrease.
Decrease, right?
Yes.
The voltage will decrease. And at a certain loading, the voltage will collapse. This is the critical point. This is the collapse point. In general, in a steady state, loading is 100 megawatt, for example, and the voltage is 1.0 or 0.99 per unit. If you start increasing the loading, definitely the voltage will collapse at this critical loading. The voltage stability is simply gives you how far from this collapse point you are. When you check the stability, it gives you what is the distance for how much you can increase your loading before your system will collapse. So voltage stability is V versus B. Okay, so this is the voltage stability. Voltage stability is mainly related to the reactive power in the system. And in this problem, we are handling the. Of course, we have two types of voltage stability. We have static voltage stability and we have dynamic voltage stability. And if the system is in severe condition, so we need to have dynamic. And if the gradually change in the loading and so you can linearize the system and you can say the static voltage stability. So this is the voltage stability. The frequency stability, this is another stability problem in power system. How the frequency will change with the load. How the frequency will change with the load. This is the frequency. Okay. Usually the frequency is, as such, around 60 hertz here in Saudi Arabia. If you have a disturbance, in this case, if you have load increase or load decrease, in this case, you have a disturbance in the frequency. You have, if the load increases, definitely. If the load increases, the frequency will drop. And if you have the governor will help. The inertia of the machine will help here. And if you have also a primary, secondary, tertiary, reserve, in this case, the frequency will go back to 60 hertz. So it is AGC or frequency or load frequency. We call it load frequency or automatic generation control problem or load frequency problem. So this is the frequency stability. The time frame of these are different. And here for angle stability, we are talking about few cycles after the disturbance. Few cycles after the disturbance. It's cycle, and one cycle, is approximately 16.67 milliseconds. And the time frame here for the angle stability, if it is transient, on angle stability again, we have three types of angle stability. We have steady state stability, we have dynamic stability or low frequency stability, and also we have transient stability. So the range, the time range here, you are interested in studying the system performance immediately after the fault, 1 cycle, 2 cycle, up to 1 second, 2 seconds. So this is the period where you want to check the angle stability. And voltage stability could be in minutes. And frequency or load frequency also could be in minutes. And time frame of those type of stability is longer than what we will cover here in this course, which is the angle stability. Okay. Any question? Okay. How to improve the power system stability? And if we have a problem in the system, how to improve? What are the tools for the power system operator to enhance the system stability? What do you think? Any idea? Any suggestion? Nasser Hakami? Yes?
Spinning reserve, increase the spinning reserve in the system.
Increase the spinning
Reserve.
reserve. Okay, great. طبعا الspinning reserve, if you have a spinning reserve and you have any disturbance in the load increases or decreases, so in this case you are in better shape. Especially if the load increases and you have enough reserve to cover, so this will improve the stability. What else?
Still more.
Yeah, of course. You have, and if we start listing all these issues, and long list, we have long list to improve the stability. The power system operator, of course, you can classify the methods to improve the power system stability. To planning phase, you can improve the power system stability in operation phase, and so on. Long term, short term. طيب نشوف حسين علي.
Yes, doctor. Actually, you could improve the power system stability by fastly clearing any incident or fault.
Okay, you are right. This is if you can, you have a protection system, fast
Yes.
protection system. Of course, لأنه in power system, and probably for those who covered the stability in 520, you heard about critical clearing time, right? Critical clearing time.
Yes.
If you have a fault applied, and if you don't take any action to isolate the fault until you reach to this critical clearing time, your system will be unstable. So one way to improve the system stability is to have fast protection system in order to isolate the fault as early as possible and not to exceed this limit. If you exceed this limit, يبقى العوض على الله في السيستم. The system will be unstable, and if the system becomes unstable, then the protection of the generator will operate. It will isolate the generation, and eventually, either if you have even an interconnected system, the interconnection link will be, of course, isolated, and both areas will experience generation load imbalance, and this also could lead to start tripping the power plants here and there, and eventually you can reach to blackout. Okay, so if you have fast protection system, in order to isolate the fault before reaching to the critical clearing time, in this case, you can improve the stability of the system. Okay, fast protection will help. What else? Ramadan Ali.
Yes. What about having or designing capacitor banks and additional transmission lines? I believe it will improve the overall power system.
Okay, you can, instead of having this capacitor bank, in the capacitor bank we have other devices which behaves in a better way than the capacitor bank. You can have a static VAR compensator, you can have STATCOM for SVC, static VAR compensator, you can have STATCOM, static synchronous compensator, or in general shunt compensation. يعني خلينا نقول بقى ايه الكاباسيتور embedded here ان شاء الله. الكاباسيتور الاس في سي الستاتكوم shunt compensation in general. If you have shunt compensation, of course, this will help in improving the stability of the system. Shunt compensation. Okay. This is CVC and the STATCOM. Sometimes probably you heard about FACTS devices. FACTS devices. These are some kind of FACTS devices. FACTS devices, flexible AC transmission system. You have flexible AC transmission system. Why it's called flexible transmission system? Then simply when you have two buses here, the power between bus 1 and bus 2, the power flow V12 is equal to V1 V2 over X12 sine delta 12, isn't it? This is the power flow between bus 1 and bus 2. Here, if you have one of those devices, and also for others, you have other devices also. These are shunt devices, but you have also series devices, and you have also both shunt and series devices, like Unified Power Flow Controller, series devices like TCS. We can say here series also, series compensation, like TCSC, thyristor controlled series capacitor, and SSC, this is static synchronous series compensator. These are also our FACTS devices. In addition to, of course, the classical capacitor also. You can have a series capacitor. Here you have shunt capacitor, and you have here series capacitor for series compensation. So such elements will improve the system stability. Let me give you a very simple example. If you have a capacitor here, this line 1, 2, and this is the power V12 equal to V1, V2 over the reactance of the line. You have here X12 sine delta 12. Type. If you have a capacitor here, if you add a capacitor here series, you have an XC, and this is X12, and this is bus 1, and this is bus 2. What is the total capacitor? What is the total reactance here for this? If you have such series compensation, what is the total capacitor? X12 minus XC, right? X12
Yes.
minus XC. If you have X12 minus XC, this is the total reactance here. So in this case, you have X12 minus V12 in this case equal to V1, V2 sine over X12 minus XC. So in this case, you increase the power transfer between bus 1 and the bus 2. And just to, to get the, sensible numbers, if you have XC capacitor reactance, half of the line, half of the reactance of the line. And X12 minus XC will be half of X12. In this case, adding this capacitor will double the power transfer. Will double the power transfer, as if you install another transmission line here. And adding this capacitor is similar to adding a complete transmission line. And this is why we have here in Saudi Arabia, between Eastern operating area, and you have here Central operating area, and also you have a capacitor bank here in series with the Western operating area. So you have these capacitor banks. These are the, of course, this is the classical capacitor. But if you need more, flexibility, you can replace this by thyristor controlled series capacitor, or by the more advanced, FACS devices, or second generation, which is static synchronous series compensator. So this is the series capacitor here. So this is very important, shunt compensation. Series compensation will help also for improving the power system stability. What else? Any other? Muhammad Tagisser.
I think in the operation side, we can increase the system flexibility by adding more flexible loads, adding energy storage systems, and so. This is in the operation side. In planning side, we can add, for example, the N-1 contingency technique.
Okay, so you have energy storage. Yes, the energy storage will help in improving the system stability, definitely. N-1 is the rule for, the security. Of course, you have to analyze the security of your system after, tripping one element, either transmission line or generator. You need to have all the system constraints not violated. So N-1 rule is used for security analysis. Of course, if your system is secure under N-1 rule, or N-2, لو N-2 يبقى أفضل وأفضل, is much better than N-1. N-2 means no, there is no system violation under tripping of two elements. N-2, two elements, like two transmission lines, or two generators, or one generator and one transmission line. If your system is secure under N-2, your system will be very, very strong. But N-2 is not a big issue. N-2 is simply the one tower. If one tower is hit or damaged, so usually the transmission line carries out two lines. Am I right? And you have here one circuit, and you have here also another circuit. So this is transmission line, and this is a transmission line. So if this tower is damaged, or this, one tower represents N-2 security. Okay. So if your system can overcome such a disturbance, your system is very good or strong. طيب Nasser, do you have another way to improve the stability of the system?
Yes, increase the system stiffness and increase the inertia by interconnection between countries.
You are right. The interconnection is very important.
So inertia will increase and the system will stand during the short circuit.
You are right. Yes, the interconnection will, of course, enhance the system stability. طيب عبد العزيز خالد.
Yes, Doctor. This is a case I'm not 100% sure about it, but maybe you can shed some light. Having dummy loads or load banks in case of when the generator example is oversized or the load is underestimated, or you have a major shutdown in your plant and you want to keep the generator running.
In this case, what we are talking about, Abdulaziz, is what we call the braking resistors. When you have a generator, and this generator, you have an electrical power, VE output equal to V times I, and you have V mechanical here. In general, in a steady state, without loss of generality, assuming the power loss equal to 0, معناها الefficiency is 100 for the generator, يعني ال B mechanical equal to B electrical. Okay? B mechanical equal to B electrical. طيب, now if suddenly you have a fault somewhere here and the voltage collapse, voltage here becomes 0. Assume that is the solid fault, solid 3-phase fault. So how much of the power here, which is V times I? 0. So you have here B mechanical comes from the turbine, and the output power here during the fault equal to 0. So we have unbalance now between B input and B output. So where B mechanical will go? Where B mechanical will go? Where?
There will have to be a dummy load. Yeah.
You can see the swing equation plays a great role in power system dynamics and stability. You have md square delta by dt square equal to B mechanical minus B electrical. If this becomes 0, معناها انه this is the acceleration, and the B mechanical now has a value, and this difference here becomes positive. And if it becomes positive, then the machine will accelerate. The rotor of the machine will accelerate. That means that B mechanical is converted to kinetic energy. It's converted to kinetic energy. And the rotor will start to accelerate. The omega will start to increase. The speed will start to increase. وبالتالي الفريكونسي will increase. The frequency will increase, and of course, you will not keep the frequency increases, beyond, for example, 60 point or 61 or something. In order to improve this case, when we have a fault here, we can طبعا isolate the fault, and then we can switch on some variable resistance. This is called the braking resistor. And you add here like a dummy load, as you mentioned, Abdulaziz, a dummy load here in order to absorb the real power here and try to minimize the difference of this B mechanical minus B electrical. Now we have B electrical output. This is called the braking resistor. And this braking resistor you have here like electronic switches. And it is not, connected forever. This is only for during the disturbance, when we have a problem. you have here electronic switch like thyristor. So you have this resistor connected to the system and switched off, connected and switched off. In a few milliseconds you connect them, and after a few milliseconds you switch them off. Of course, you have here huge power dissipated. Huge power dissipated here in this resistor. You cannot connect the resistor, but you can switch on off in order to improve the system stability and reduce the frequency from being violated. Okay, this is a braking resistor. What else? Opposite to this, you can have under frequency load shedding. Under frequency load shedding. Okay. The opposite way around. If you increase here the load, then the frequency will start. If VE is greater than V mechanical, if you increase the load, then the rotor will start decelerates. And in order to improve the situation here, you can have under frequency load shedding in order to shed some loads, to disconnect some loads, to reduce the V mechanical in order to bring the frequency back to 60 hertz. In order to have, the main issue that we will cover here in this class or in this course is a power system stabilizer. This power system stabilizer is a controller in the excitation loop, as we mentioned here. And we have here excitation loop. We can have a controller here. This controller is called the power system stabilizer, and this will help in improving. We will see how to design this power system stabilizer and see. Of course, we have different types of measures in order to improve the power system stability, and we will cover them, from time to time during the course. Okay. Now this is the power system stability. This is the angle stability. In order to be specific, the main coverage of this course is the angle stability. This angle stability can be divided to two types of stability: steady state stability and the transient stability. And this depends on the size of the disturbance. If you have a small disturbance, gradually change in load, and so on, so you are talking about not severe disturbance, and this is the steady state stability. If you have a severe disturbance like faults, like tripping heavy loaded line or big load, so this is a transient stability problem. It depends on the size of the disturbance. We can classify whether it is a steady state or transient. In transient stability, we cannot linearize the system around an operating point. So we will handle the equations or the dynamics of the system as it is, including the nonlinearity there. But if the disturbance is gradual disturbance, so you can linearize the system. So we have here like steady state, static stability, and also dynamic stability. In this case, you can have algebraic equation. Here you can have linearized model. So this will be the stability classification that we will cover in this class, inshallah. Why this course is important? Usually you have continuous changing in load and so on. So disturbance, you have several disturbance in power system like load change, protection operation, and faults, and all these issues, needs to represent the system not by algebraic equation like in steady state problems, but in dynamic or differential equations. But this is important due to the nature of the loads and so on. Power system stability, the ability of the electric to regain, this is the definition, to come back to an equilibrium point after being subjected to a physical disturbance. It is possible also for the power system frequency to become unstable, and generating units and or loads may ultimately be tripped, possibly leading to the system blackout. So you have to keep the generation and load. This is the swing, and you have here load and generation. So you have to keep this swing balance. Otherwise, your frequency will be in trouble. And then if you have some protection start operating, you may lead to blackout at the end. Another important point these days, the power system stability becomes more and more important due to the high penetration of renewable energy sources. This, of course, definitely the intermittence nature of the PV and wind will, of course, negatively affect the power system stability. And also, if you start replacing the synchronous generator with the distributed generator or generations, inverter based, you have power electronic, interface between the PV and wind and so on. The high penetration of this type of distributed generation also will reduce the inertia of the system. This M, okay, let us write it here. Again, back to the swing equation. M is called the inertia, and the d square delta by dt square equal to B mechanical minus P electrical. So this is the inertia. Well, inertia is related to the mass. So if you have synchronous generator, and in this synchronous generator or generation plant, the rotor, if you can imagine how much the rotor weight, rotor can reach to 50,000 tons. So this is the rotor mass. So you have here a huge moment of inertia for the synchronous machine. So this inertia here will reduce or eliminate the small changes here. And now the acceleration equal to Bm minus Be over M. So if M is very huge, then this disturbance could be neglected. But if you start reducing or start replacing the conventional generation by this distributed generation, which has no inertia, there is no inertia here for the PV and wind. When it is interfaced with the inverter or power electronic switches, in this case there is no inertia for this, and this M will start reducing, and in this case we have a frequency problem. So we need also to study the power system stability during the due to the penetration of this renewable energy sources. Quickly, let us go to the course description. Introduction to power system dynamics. We will do some mathematical modeling for synchronous machines, as we mentioned, for field exciters or automatic voltage regulators, for prime movers, turbines, and governors, and so on. For loads also, loads can be represented in different way, like impedance, constant power, constant current, voltage dependent, frequency dependent. You have several representation of the loads, and we will see also the impact of the load representation on the power system stability. So we will see the angle stability in 3 times: steady state stability or static stability, small signal or low frequency oscillation or dynamic stability, and also we have transient stability. And the difference between those are the the severity of the disturbance. Power system stabilizer design, we will see it, and also the improvement of the power system stability, how to improve the power system stability. Of course, objectives is, at the end of the course, I hope you will be able to assess the stability whether of a large interconnected system or multi-machine system and single machine infinite bus system. You gain understanding of the dynamic performance, and you can propose some of the remedial actions. Depends on the system situation. The outcomes, you will see how to model the different elements and how to improve the stability, how to formulate the problem, how to design the controller. All this will be covered here. I hope definitely most of you covered the 520, which is power system steady state analysis. We need it. Like when we say power per unit normalization, load flow, you know what is load flow. If you have symmetrical components, fault studies, swing equation, equal area criteria, all these have been covered in power system analysis. And control engineering also, and we need some of the design of the power system stabilizer or the controller. You need to have some background. You need to refresh your background in frequency response techniques, and analyze the system performance, time domain analysis, the overshot, undershot, and the damping coefficient. You need also to know what is the damping coefficient and so on. For the controllers or compensation or compensators, you have lead lag compensators, BI, proportional integral, derivative controllers also. You have to have some background on this. And from time to time, we will cover, or we will say something related to BID, something related to lead lag. You need to go over this, the first course in control. You have different references here, electric power system dynamics. Hadi Saadat also cover, Hadi Saadat book, which is used in 520, also 463. Undergraduate is covering a good part of the steady state stability and transient stability. We have another book, which is the power system dynamic stability here. And the Kondur book, this is a good reference for power engineers in general, not only for the dynamics part. Granger and Stevenson also, this is a good book for transient stability. Anderson and Fuad also, we have a good book on stability. So this is the coverage. I think the time is over. These are the topics and distribution of the weeks. There's nothing to be explained here. This is the distribution of the grading. Since we have midterm exam and the final exam in person or face-to-face, then we have 20% here and 30% here. Quizzes and homeworks, 20%. We have reading assignment, which is 10%. We will give you like a topic, and we ask you to read about it, and then you can do some kind of presentation on this. And also the term paper is 20%. The exam, I think the registrar will assign the date for the exam and the time in order to organize with other courses. And I think let us stop here. Lena, time is over, and we can, discuss this. طبعا we will use the blackboard, and I posted some material there, syllabus and so on. But probably I changed this from 25 from the syllabus posted in Blackboard to 20, and I increase this to 30%. Okay, this is the only change from the syllabus outside. We will talk about the reading assignment and term project and how to proceed later on, inshallah. If you have any question, please ask. If you don't have, then you can log out. But let me at the beginning, first before leaving, take the attendance. And the attendance here will show me the when you log in, when you log out, and so on. So everything is recorded here. Okay, so if you have any question, please stay with us. If you don't have, then you can leave. Hello, شباب. معايا ولا Yes, please.
Yes, the term project is individual.
The term project will be on group basis. We have like 10 students or 11 or 12 students maybe. And in this case, we have like 5 groups, 2 students per group. We encourage group work. Of course, you can team up from now in terms of the reading assignment and term project and so on. Okay. Any question? Any other question? If you don't, okay, thanks a lot. Okay. I will stop recording here.